Welcome back to the Bootstrapped AI Podcast for another episode in our neural knowledge series. We're breaking down that the techie side of AI for everyday users.
Right.
And today we're diving deep into neural networks.
Okay.
In an episode we're calling Neural Networks. Let's think about thinking.
I like it.
So,
you
know, it's a fitting title. Considering neural networks are essentially these complex mathematical systems that are modeled after the human brain.
Right.
And they're designed to learn from data.
Yeah.
Just like we learn from experiences.
Exactly.
So instead of picturing a physical brain, when I hear neural network, should I be thinking more about equations?
Yes.
And algorithms?
That's a better way to think about it.
Okay.
Yeah, imagine like a network of these interconnected nodes that are organized in layers. And these nodes, they're like artificial neurons. And the connections between them, they have these things called weights, which determine how strong the signal is passing through. So during training, those weights get adjusted so the network can learn from the data.
So it's less about the physical structure.
Yes.
And more about the math.
Yeah, it's more about this complex mathematical dance.
So it sounds like you're fine-tuning this machine.
Yes.
Where the network is figuring out the best path for data to flow through.
Yeah.
By like tweaking those connections.
Exactly.
It learns to make predictions.
That's right.
But where did this whole idea even come from? Like who thought of this in the first place?
Well, the concept goes all the way back to 1943.
Wow.
With Warren McCullough and Walter Pitts. And they were trying to understand how neurons could compute using something called threshold logic. So basically, a neuron only fires or sends a signal if the input it receives exceeds a certain threshold, which was a revolutionary idea at the time.
That's amazing, considering computers as we know them didn't even exist back then.
Yeah, it was pretty early on.
So what happened next? Did someone actually build a neural network?
Yes, they did.
In
1957, Frank Rosenblatt built upon that idea and developed the perceptron. It was the first trainable neural network that could learn to classify patterns.
Wow.
So think about it. A machine that could learn. That was a huge breakthrough.
So with a concept this groundbreaking, I mean, it must have been just a straight shot
to
the advanced AI we see today, right?
Not exactly, no.
Right.
There were these periods of what we call neural network winters.
Neural network winters.
Yeah, where research and funding slowed down. Like, for instance, in the late 1960s, researchers Marvin Minsky and Seymour Papert, they highlighted some limitations of the early perceptrons, particularly their inability to solve certain types of problems. And their work actually led to a decline in enthusiasm and funding for neural network research for a while.
Oh, wow.
Yeah.
So how did researchers eventually overcome those limitations?
Yeah.
What pulled neural networks out of the shadows?
Well, one of the biggest breakthroughs came in the 1980s. With the development of the backpropagation algorithm. And this algorithm allowed for the efficient training of multi-layer networks, which was a crucial step in overcoming the limitations of the earlier models. You can think of it as like a feedback mechanism, where the network learns from its errors and adjusts the weights of its connections to make more accurate predictions.
So backpropagation essentially opened the door for more complex networks.
Yeah, that's a good way to think about it.
Paving the way for the deep learning that we see today.
Yeah, exactly.
So, but the real explosion happened in the 2010s, right?
Yeah, pretty much.
When powerful GPUs capable of handling complex computations became more readily available. And you combine that with the rise of the internet and the massive amounts of data suddenly available. And you have like the perfect storm for deep learning to take off.
That's right.
So we've got the history. We've got the basic concept of how neural networks work. But it sounds like there are many different types of neural networks.
There are, yeah.
Is that right?
You're absolutely right. There's a whole family of neural networks out there. Each designed for specific tasks. So the perceptron we talked about earlier is like the most basic type. Then you have feed-forward neural networks. Or FNNs, where information flows in one direction from input to output, kind of like a one-way street.
And I keep hearing about CNNs.
Yeah.
Those are the ones that are used in self-driving cars.
Yeah, that's a good example.
And things like that, right.
Exactly.
Yeah.
Those are convolutional neural networks.
Okay.
They excel at processing visual information like images and videos.
Okay.
They analyze data in these small chunks, which makes them incredibly good at things like object detection and facial recognition.
Okay.
So you can think of them as like the visual artists of the neural network family.
And what about RNNs?
Yeah.
I've read that they're good at language processing. Do they work differently?
They do, yeah.
Okay.
Recurrent neural networks, or RNNs, they're unique because they have a sort of memory.
Okay.
This means they can process sequences of data, like the words in a sentence, making them ideal for natural language processing tasks like translation or generating text.
So if CNNs are the visual artists, RNNs would be like the poets.
Yeah, I like that.
Or the writers.
Yeah.
Yeah, I'm starting to grasp this diversity of neural networks.
Yeah, it's a pretty diverse field.
But let's go back to the learning aspect for a moment.
Okay, sure.
We keep talking about networks learning from data.
Yeah.
But what does that actually mean? Is it really magic?
It's not magic.
Or is there like some serious math involved?
It's definitely not magic, although it can sometimes feel that way.
Okay.
It all boils down to math.
Okay.
But don't worry, you don't need to be a math whiz to understand the basic concepts.
All right, I'm ready to try.
Okay.
And decode the secrets of neural network learning.
All right, let's do it.
Let's dive in.
So the foundation of it all is linear algebra.
Oh?
So imagine data like being translated into numbers and then manipulated through a series of calculations.
Okay.
That's essentially how neural networks represent and process information.
So linear algebra is like the language.
That's a great way to put it.
That neural networks use to understand the world.
Exactly.
And then comes calculus.
Yes.
This is where the real learning happens.
Exactly. This is where the magic happens.
Okay.
Neural networks learn by minimizing a loss function, which measures how far off their predictions are from the actual values.
Yeah.
And calculus helps them figure out how to adjust the weights of their connections to improve their accuracy.
So calculus is like the coach.
Yeah.
Helping the network fine-tune its performance.
Yeah, that's a good way to put it.
And learn from its mistakes.
Yeah.
What else is involved?
Well, we also have optimization algorithms. Think of them as like personal trainers for the network, finding the most effective ways to adjust those weights based on the feedback from the loss function.
It's fascinating how all these pieces work together.
Yeah.
It's like a whole orchestra of math making this learning process happen.
That's a great analogy.
And that's just, you said, scratching the surface.
Yeah, we're just getting started.
We also need to talk about activation functions.
Yeah, we do.
Which add another layer of complexity.
Right.
And allow neural networks to learn more complex patterns.
Exactly.
But we'll save that.
Yeah.
For the next part of our deep dive.
Good idea.
This is already blowing my mind.
I know, right?
I can't wait to hear more about those activation functions and how they fit into this mathematical puzzle.
We'll definitely get into that next time.
Awesome.
Yeah.
All right, so before we were talking about this fascinating world of math that powers neural networks.
Yes.
We've got linear algebra as the language, calculus as the coach, and optimization algorithms as the personal trainers.
That's right.
What were those activation functions you mentioned?
Oh, yeah. Those activation functions, they introduce nonlinearity into the network.
Okay.
Without them, the network would only be capable of simple linear calculations, which would really limit its learning capacity.
So instead of just like adding and subtracting, the activation functions kind of spice things up a bit?
They do.
What do they actually do?
Essentially, they determine whether a neuron should fire or not based on the input it receives. You can think of them as like gatekeepers, deciding which information is important enough to pass along.
Okay, that makes sense. It's like a filter, making sure only the most relevant signals get through.
Exactly.
What are some examples of these activation functions?
Some of the popular ones include sigmoid ReLU, which stands for rectified linear unit.
Okay.
And TON. Each one has its own strengths and weaknesses. And choosing the right one often depends on the specific task that the network is designed for.
So it's like choosing the right tool for the job.
Yeah.
Making sure the network has the right kind of filter.
Exactly.
For the data it's working with.
That's a great way to put it.
And when you combine these activation functions with the linear algebra, the calculus, the optimization algorithms, you have this powerful system capable of learning complex patterns from data.
Exactly.
It's incredible to think about all this intricate math happening behind the scenes.
Yeah.
Every time we interact with AI, like when we use facial recognition to unlock our phones,
right,
or ask a virtual assistant a question.
It's pretty amazing.
It is remarkable how far this field has come.
It really is.
But like any powerful technology, neural networks have the potential for both positive and negative applications.
That's true.
Right? With all this incredible potential comes a need for careful consideration.
Yeah.
About how these networks are developed and used.
Absolutely.
What are some of the challenges we need to be thinking about?
Well, one of the biggest challenges is ensuring that these networks are used responsibly.
Okay.
It's crucial to be aware of potential biases and to develop strategies for mitigating them.
So even though we're talking about math and algorithms, human values still play a crucial role.
Absolutely. We need to think carefully about the data we use to train these networks.
Okay.
And ensure that it's representative and unbiased. We also need to develop methods for understanding how these networks make decisions.
Yeah.
So we can identify and address any potential biases that may emerge.
So it's not just about the technical aspects,
right,
but also about the ethical considerations.
Yeah, exactly.
We need to make sure these powerful tools are used for good.
I completely agree.
It sounds like ensuring responsible AI development is a complex and multifaceted challenge.
It is.
Requiring expertise from various fields.
It really does.
But let's shift gears for a moment and look ahead to the future of neural networks.
Sounds good.
What are some of the exciting developments and research areas that have the potential to push the boundaries of what's possible with neural networks?
There are many exciting directions.
Okay.
One area that's generating a lot of buzz is explainable AI, or XAI. Researchers are working on ways to make the decision-making process of neural networks more transparent and understandable.
That makes sense. The black box problem you mentioned earlier, where we don't always know how neural networks arrive at their conclusions, can be a major obstacle.
It can.
Especially in sensitive areas like healthcare or finance.
Absolutely.
Explainable AI aims to address this by providing insights into the reasoning behind AI decisions. Building trust and allowing for better accountability.
Exactly.
That's crucial, especially as neural networks become more integrated into our lives.
I agree.
What are some other promising areas of research?
Another exciting area is federated learning.
Okay.
This approach allows neural networks to be trained on decentralized data sets without the data ever leaving its original location.
So it's like learning from multiple sources without actually bringing all the data together in one place.
That's a good way to think about it.
That's amazing.
It is.
And what about those quantum neural networks you hinted at earlier?
Oh, yeah, quantum neural networks. Yeah. They're still in their early stages.
Okay.
But they hold incredible potential. They leverage the principles of quantum mechanics to perform computations that are currently impossible for traditional computers.
So it's like combining the power of neural networks with the mind-bending capabilities of quantum mechanics.
Exactly.
Wow.
Yeah.
Quantum neural networks have the potential to revolutionize fields like drug discovery materials, science, and even our understanding of the universe itself.
It's pretty amazing stuff.
Wow, that sounds almost like science fiction.
It does a little bit.
It's incredible to think about what might be possible in the future with these advancements.
I know.
But before we get too carried away, let's take a moment to recap what we've covered so far.
Okay, sure.
We've explored the fascinating history of neural networks, from their humble beginnings with a perceptron to the explosion of deep learning in recent years.
Right.
We've delved into the intricate math that powers their learning process, from linear algebra and calculus to optimization algorithms and activation functions.
It's a lot to take in.
And we've touched upon the ethical considerations surrounding their development and use, as well as the exciting future possibilities with explainable AI federated learning and even quantum neural networks.
It's an exciting field.
It's been an incredible journey through the world of neural networks so far.
It really has.
But there's still one important question we need to address.
Okay, what's that?
So we've talked about the history, the math, and even like glimpsed into the future of neural networks.
We have.
But if they can already do so much, from like recognizing faces to composing music, what are the limits of what they might be able to achieve?
That's the big question.
Where does this all lead?
That's a question that keeps researchers and thinkers up at night.
Yeah.
It's almost like we've discovered this incredible tool, but we're still figuring out all the ways it can be used.
So it's not just about improving the existing technology,
right,
but also about like exploring entirely new applications and possibilities that we haven't even imagined yet.
Exactly.
Wow.
Think about the early days of the internet.
Okay. Yeah.
No one could have predicted the explosion of social media or e-commerce,
right,
or the countless ways it would transform our lives. It's the same with neural networks.
Yeah.
We're just scratching the surface of their potential.
It's both exciting and a little bit daunting to think about, isn't it?
It is.
It's like we're on the verge of a whole new era of technological advancement.
I think so.
And that's why it's so important to have these conversations, to think critically about the implications of this technology.
Oh, absolutely.
And ensure that we're developing it responsibly.
I agree.
So it's not just about the technical advancements.
Right.
It's also about the ethical and societal implications. We need to be mindful of the potential impact on jobs, privacy, and even the very fabric of our society.
It's a big responsibility.
Absolutely. We need to approach this with a sense of responsibility.
I agree.
Asking ourselves these tough questions about the values we're embedding in these systems and the kind of future we want to create.
That's right.
It's like we're holding the keys to a powerful engine.
Yeah.
And it's up to us to decide where we want to go with it.
I like that analogy a lot.
And as we navigate this uncharted territory, we need to remember that this is a journey we're all on together.
Absolutely.
It's not just up to the scientists and the engineers.
Right.
It requires input from ethicists, policymakers, artists, everyday citizens. Everyone has a role to play.
It's a collective effort.
So it's about fostering a dialogue, a collective conversation about the direction we want to steer this technology.
Exactly.
And that dialogue needs to be open, inclusive, and informed.
Absolutely.
We need to educate ourselves about the potential benefits and risks of AI, engage in thoughtful discussions, and work collaboratively to shape a future where AI serves humanity in these positive and meaningful ways.
I think that's a great goal.
So to our listeners, we leave you with this challenge.
Okay.
Stay curious, stay engaged, and join the conversation about the future of AI.
It's important.
Your voice matters.
It really does.
And that's a wrap on this episode of the Bootstrapped